So we've just said a bunch of things about a very special kind of matrix. The type of matrix we've been talking about so far is called reduced row echelon form. And those matrices are incredibly nice because the structure there is so rigid that we can really say a lot of interesting things about those matrices. There are other matrices that are slightly less nice, but still pretty nice to work with. And the next form of that type of matrix I want to talk about is what's called row echelon form. So note here we're sort of dropping the adjective reduced. So you could also think of this as non-reduced or not necessarily reduced row echelon form. So here the rules are slightly different but similar. So again, let's say we're working with an m by n matrix called R. You'll notice right away that this matrix is not in reduced row echelon form. It is, however, in row echelon form, and let's see why. So we say that our matrix is in non-reduced row echelon form, or just row echelon form, if, 1, any 0 rows occur at the bottom, so that's the same as the first rule for reduced row echelon form. In this example, we have 1 row of zeros, but it is at the bottom, so we're not worried about it. The second rule says that the first non-zero entry of the other rows is just called the pivot. We don't care what it's equal to. This is our first departure from reduced row echelon form. In reduced row echelon form, all of the pivots have to equal 1. In row echelon form, so non-reduced row echelon form, we don't care what the pivots are equal to. So you could tell right away this matrix is not in reduced row echelon form because the very first entry of the first row is not equal to 1. But to be in row echelon form, we don't actually care what that entry is equal to. That's our first pivot. It's equal to 9. It lives in the 1, 1 position. In the second row here, we start with 2 zeros, which is fine. And then the third position is equal to 3. That's great. That's our second pivot. In the third row, we start with 3 zeros, and then we get 6. That's our third pivot. So again, this would be bad if we were looking for reduced row echelon form, because in reduced row echelon form, we need to have pivots equal to 1, but in non-reduced row echelon form, we don't care what the pivots are equal to. Great. So far, so good. We have a row of zeros that's at the bottom. We have pivots. We don't care that they're not equal to 1. Number 3, the third axiom for row echelon form says that every pivot has to occur to the right of pivots above it. This is exactly how reduced row echelon form works, except again, we're not requiring that the pivots equal 1. So if we look at how the pivots are structured here, this is great. To get from the first to the second, we travel right and down, good. To get from the second to the third, we travel right and down, also good. So the third axiom passes here. And what about the fourth axiom? The fourth axiom for row echelon form, so not reduced, but just row echelon form, says that all entries below a pivot have to equal 0. Remember, in reduced row echelon form, we said that the pivot can be the only non-zero entry in the whole column. For row echelon form, so not necessarily reduced, we're only requiring that the entries below pivots are equal to 0. And we'll see here that this actually works. Our first pivot is in the 1, 1 position. It's equal to 9, but we don't care. And every entry below it is equal to 0. Good. If we look at the second pivot in our matrix here, it's equal to 3, but again, we don't care because we're not looking for reduced row echelon form. We just want to be called row echelon form. And we have an 8 above it, and that would be bad if we were looking for reduced row echelon form. But in row echelon form, I don't care what's above pivots. I only care that there are zeros below pivots. So here, below our second pivot here, we get all zeros. That's great. And then finally, for our third pivot here, that's equal to 6, but that's fine. There are non-zero entries above it, but that's also fine. But the only entry below it is equal to 0, so that works. So all entries below pivots here are equal to 0. So now that's all the axioms. This matrix is in row echelon form. So reduced row echelon form is something more strict than just row echelon form. And you can sort of tell here, because the rules are more strict for reduced row echelon form things are easier to work with. But as we'll sort of find out as the course goes on, Reduced row echelon form requires more effort to find sometimes, and sometimes it's easier just to find row echelon form, which is not quite as nice as reduced row echelon form, but it's still pretty nice. So let's do some examples here. Here we have a matrix, and it's got lots of rows and lots of columns. Is it in row echelon form? Well, we start with 2 rows of zeros at the bottom. So there are rows of zeros, but they're at the bottom, so that's totally fine. We have pivots here, and here it looks like we have 3 of them. So these are the first non-zero entries of rows that are not all equal to 0. And remember, in row echelon form, we don't care what the pivots are equal to. In reduced row echelon form, they all have to equal 1. Here, we don't care. So our pivots happen to equal 5, -2, and 14. That's fine. Do they occur? Does every pivot occur to the right of the pivots above it? Yes. To get from the first to the second, we travel to the right and down. To get from the second to the third, we travel right and down. And then finally, is every entry below a pivot equal to 0? Yes, in this case. So this is an example of a matrix that's in row echelon form. Also, this matrix is in row echelon form, but of course it is not in reduced row echelon form. The pivots aren't equal to 1, and they're also not the only non-zero entries in their respective columns. So this is in row echelon form. It is not in reduced row echelon form. Here's another example. So here we do have a row of zeros. It's at the bottom. We have pivots. In this case, the pivots are 2, 3, and -4. Every pivot occurs to the right of all the pivots above it. And every pivot is has all zeros below it. So this is another example of a matrix that's in row echelon form. And of course, this one's also not reduced row echelon form. The pivots are not equal to 1, and there's also some of the pivots have non-zero entries above them. Here's another example. So here we have 2 rows of zeros at the bottom. We do have pivots. Again, they're not equal to 1, but since we're only looking for row echelon form here, that's fine. The pivots are also the only, or everything below a pivot here is equal to 0, so that's cool. But of course, the problem here is that to get from the second to third pivot, we have to travel to the left and down. So even though this matrix is close, it is not in row echelon form. So cross it out. The last thing I want to mention here is that even though the rules for row echelon form are less strict than the rules for reduced row echelon form, we still get all these concepts like rank and nullity. So the rank and the nullity is the same thing as the number of pivot columns and non-pivot columns. Since we have pivots to work with in row echelon form, all of that language makes sense. So here we have a matrix that's in row echelon form. Our pivots here are 7, 3, and 6. So these are in the 1, 1, 2, 2, and 3, 4 positions. So clearly here we have 3 pivot columns. And so we would say here that the rank is 3. And then we have 2 non-pivot columns. And so we would say that the nullity here is equal to 2. So all of these concepts carry over to the concept, to the world of row echelon form matrices that aren't necessarily reduced. Which is nice. So again, row echelon form is less strict than reduced row echelon form, which comes with some benefits because we'll find later that it's easier to find and quicker for calculations. But it's also not as nice because it's like you can see for yourself, it's much harder to derive things like column relations for matrices that aren't in reduced row echelon form. So we're going to be working with both of these types of matrices throughout the semester. We'll do more with reduced row echelon form stuff, but we'll still do plenty with row echelon form stuff. And like those of you who might be interested in like numerical linear algebra down the road or more computer science and algorithm writing, I want us to make sure we see row echelon form because that is more useful for efficient calculations.